Hello dear students, in this lecture we will continue our discussion on ion acoustic waves. In the last class we have seen that we can derive the dispersion relation between omega and k like this, and the omega by k, which is the phase velocity of the ion acoustic wave, was derived like this. So, we will take this expression ahead. We will write omega by k, the angular frequency divided by the wave vector, is equals to kb Te plus gamma I kb Ti divided by mi. So, where kb is the Boltzmann's constant, gamma is the ratio of specific heats for ions, Te and Ti are the temperatures of electrons and ions respectively, mi is the mass. Now, more importantly, this will be the speed of an acoustic wave traveling in plasma. Now, one very important conclusion is, from this expression we can realize that Vp will be equal to Vg, which will be equal to a constant. Both the velocities will be the same. This is the unique characteristic of the acoustic wave that is traveling through plasma, right. So, the phase velocity and group velocity will be constants. So, we can also write this expression in a more general fashion, where omega by k is, if electron is assumed to be traveling very fast and not making any assumption that the plasma is isothermal, we can write a generalized expression as gamma E kb Te plus gamma I kb Ti divided by mi. So, this is the speed of the acoustic wave traveling in the plasma. So, the dispersion curve for the ion waves, if you see, has fundamentally a different nature in comparison to the electron plasma wave. So, in electron plasma wave we have seen that the omega versus k was something like this, and this was omega p, the minimum frequency above which, only above which electron plasma waves can exist in the plasma, and omega p is nothing but the plasma frequency. Now, if you say this ion acoustic wave, the dispersion relation will look something like this. So, this is Vs and this is k and this is omega. Like I said, velocity will be constant, right. So, for the ion waves exist only when there are thermal motions, and in electron plasma we take the ions to be remaining at rest, right. But in plasma waves, electrons are not fixed and they are not moving, they are moving very fast. Now, what is the mechanism by which this compression of the medium, which you call as the propagation of the acoustic wave, is being transported from one point to another point? It is basically the ions which are coming together and expanding as the pressure pattern is moving into the space. Now, one very important assumption that we made while deriving this is that we took the number of electrons to be equal to the number of ions, which is also called as the plasma approximation. So, you consider any plasma, the total number of electrons and ions will be the same, or we assume it to be the same, right. Now, if you make a condition saying that the validity of plasma approximation is not imposed on the plasma for the treatment of ion acoustic wave. So, we will discuss what is called as the validity of plasma approximation. Plasma approximation is when number of electrons equal to the number of ions. So, in deriving the dispersion relation for the ion acoustic wave, we have made an assumption that the electron number density is equal to the ion number density. While working out the electron plasma wave, we have considered the electron density not equal to the ion density where. So, when we were discussing the electron plasma wave, we have seen that within the small volume, from this small volume electrons were displaced out, right. And while these electrons were displaced out, the ions remained at rest because of their heavier mass, and it is the electrons which were taken out. Now, with these electrons immediately after being moved from this region will constitute an electric field, and the electrons motion will be to nullify this electric field. They will immediately boom back because of their mass, inertia or the thermal energy, if you allow it. They will execute oscillations back and forth, and this oscillation frequency is referred to the plasma frequency, right. Now, this is the initial picture that we have taken, that is basically displacing the electrons away from this, from a region where you are actually creating number of ions much greater than the number of electrons. This is the initial condition. Only this gave you a possibility to work with the Poisson equation, where you have the electric field or del dot E written as Ni minus Ne times the charge, right. So, if you do not have a valid plasma approximation, what is bound to happen? This electric field will not exist. This will be 0. This electric field will only exist when there is unequal number of electrons and ions. So, you have created it, right. Now, you realize that after doing this, plasma frequency was of course there, it was there, the oscillations were existing, but we realized these oscillations when you discuss the dispersion relation. So, you have realized that omega Pe is Ne square by m epsilon naught. What does it mean? This is the plasma frequency, we have seen it many number of times. But the important message here is that there is no dependence on the wave vector, which means there is no information passage from one point to another point. So, there is no energy transfer from one point to another point by the means of wave activity. So, the electrons are oscillating, but these oscillations or the information about these oscillations is not going into the layers of plasma. So, if you consider plasma, let us say this is a plasma system and you have different layers. For just understanding, I am drawing this. So, if the oscillations are happening here, this information is not being transported into the all the layers that are lying here, right. So, we made a altered picture where we allowed the temperature of electron to be non-zero, where the electron is now allowed to have thermal motion in addition to these vibrations, right. So, then we realized when we derived the expression for omega, we have seen it to be a function of k. What it means is that the electron now travels into the adjacent layers of plasma to tell the story of the vibrations that are happening in the first layer, right. So, this is the modified picture. So, in this modified picture, one thing is very clear, number of ions is greater than the number of electrons, at least in the small region. In the total plasma, of course not, but in the small region, number of ions is greater than the number of electrons. Now, if you go back and see the ion acoustic wave, we have imposed a condition that number of electrons will be equal to the number of ions. So, we have removed the possibility of existence of an electric field because of this condition. Now, what we are going to do is we are going to see if we allow the number of electrons not equal to the number of ions, how will it affect the propagation of an acoustic wave through the plasma, right. So, this is the basic understanding about the invalidity of plasma approximation and how it is relevant for understanding the wave propagation, especially the acoustic wave propagation in the plasma, right. Now, let us start. Let us say we have these unequal number densities. So, obviously, we will have some electric fields. Now, let us say we start with the basic equation, which is the Poisson equation. Let us say we have epsilon naught dou E by dou x is charge E times Ni minus Ne. Okay. Now, let us define the perturbation variables. N is equals to N naught plus N1. The electric field E is equals to E naught plus E1, and then we have the, let us substitute these perturbations into the Poisson equation. So, which will get epsilon naught dou E1 by dou x is equals to E times. So, it has to be n I1 plus n naught I minus n E1 plus n naught E. So, this is also supposed to be dou by dou x of E1 plus E naught. Now, because E naught is a constant, we have removed that term, or we have not considered that term. We can write, so at equilibrium we can assume the electron density and ion density to be equal. So, we can say these two terms gets cancelled. So, what will be remaining is epsilon naught dou E1 by dou x is E times n I1 minus n E1. So, these are the equilibrium terms, right, this one and this one. So, minus goes and these two terms gets cancelled. Now, we can write the electric field in terms of a potential dou square phi 1 by dou x square is equals to E times n I1 minus n E1, right, which is epsilon naught dou square phi 1 by dou x square is equals to n E1, right. So, we can take phi 1, the perturbed potential. See, what is phi 1? Phi 1 is responsible for the creation of that electric field, which is E1 also because of the disparity in the number of electrons and ions that you have imposed. So, phi 1 is, let us say, phi naught e to the power of I kx minus omega t. So, substituting this, let us say we call this equation as 2, this as 1. So, I am doing every step, I am writing every step just so that you follow the mathematics while I am doing it, and it will be easy for you to understand the implication of these mathematical steps. So, when you substitute this into that, so dou square phi 1 by dou x square will be, so dou phi 1 by dou x would be phi naught e to the power of I kx minus omega t times I k, dou square phi 1 by will be phi naught e to the power of I kx minus omega t times I k whole square. Using this, we will write epsilon naught I k square, all of this will still be phi 1 is equals to E. E is the charge in the Poisson equation, E times n I1 minus n E1. So, while writing the electric field in terms of potential, I forgot to write a minus here, because E is equals to minus del phi. So, using that minus here, so we will have this equation as minus epsilon naught I k square phi 1 is equals to E times n I1 minus n E1, right. Or removing the iota, we can write it as epsilon naught k square phi 1 is the charge times perturbed number of ions minus perturbed number of electrons. This is a very important equation that we are going to use further. So, let us say we call this equation as equation A, and from the last class actually we need to recall an equation n E1, the number of perturbed electrons is equals to equilibrium number n naught times E5 by kBt. Let us say we call this equation as B. So, this resulted from approximating the exponential, saying that E5 will be much less than kBt. So, using B in equation A. What is equation A? Equation A is the Poisson equation basically. It is written in terms of the potential phi 1. We have to substitute B into that equation. So, we will write the Poisson equation first. Epsilon naught k square phi 1 is equals to minus E n E1 plus E n I1 epsilon naught k square phi 1 is equals to minus E square n naught phi 1 by kBt plus E n I1. Just this, n naught, all of this, n naught E5 by kBt. So, okay, E phi 1 into this. So, E will multiply E square n naught phi 1 by kBte, because it is electron. We are writing TE, electron temperature. So, we can take phi 1 common and write epsilon naught k square plus E square n naught by kBte is equals to E n I1, or epsilon naught phi 1 times k square plus E square n naught by kBte epsilon naught is equals to E n I1. Now, we know that the device length lambda d square is epsilon naught kBte divided by E square n naught. Right. So, this is the factor that appears here as the second term within the bracket, seems to be resembling the device length. So, using this into this equation, we can write epsilon naught phi 1 times k square plus 1 by lambda d square is equals to E n I1, or for convenience we can rearrange the terms. Epsilon naught phi 1 is equals to k square lambda d square plus 1 is equals to E n I1 lambda d square. Let us say we call this equation as C. Right. So, what is A, what is B, what is C? Let us go back and see. Equation A is the Poisson equation in terms of phi 1. Equation B is the number density of perturbed electrons, which we have derived in the last class. If you are finding it too difficult to accept this relation, you can go back and see how this was derived. So, you have used equation number B into this Poisson equation, and then we have obtained equation number C. Now, this is still the Poisson equation, it carries the same information, but now it carries the information in terms of the lambda d, the device length. Okay, device length is a characteristic parameter which conveys a lot of information about the plasma, about the nature of plasma, or about the constituents of plasma. Now, considering what is the change that we have made from the earlier picture? We have seen that number of ions is not equal to number of electrons. The perturbed number of electrons and number of ions are not equal. Now, will this change any other equation? See, we have three equations. We have the continuity equation, we have the momentum equation, and then we have the Poisson equation. In the first picture, let us say in the first picture, the Poisson equation was not relevant because we assumed the plasma approximation to be perfectly valid, so we removed it. The momentum equation was taken and the continuity equation was taken. In the second picture, when the plasma approximation is not valid, the Poisson equation was included and it was modified in terms of lambda d. And the continuity equation, will it change because of the invalidity of plasma approximation? Of course not. So, it can be taken as it is, and the momentum equation has to be seen how it will be modified in the presence of an electric field which is created just by not accepting the plasma approximation. Okay. So, we can use the momentum equation as it is, so which is dou n by dou t plus n naught del dot u I1 is equals to 0 for the ion fluid, right. So, we know that number of perturbed electrons, number of ions can be written as n I1 e to the power of I kx minus omega t, assuming sinusoidal solution for the perturbed ions, n I1 e to the power of I kx minus omega t. So, dou n I1 by dou t is equals to n I1 minus I omega e to the power of I kx minus omega t. What have we done? We have just taken the sinusoidal solution, took a derivative with respect to time, and now we are going to substitute this back into this equation. We will continue this discussion in the next class.